Lesson 3, Electron Diffraction, de Broglie wavelengths, and the quantum model of the atom. So we're going to begin with electron diffraction. So let's revisit diffraction. Remember earlier in the course we looked at Young's double slit experiment. And the reason we study Young's double slit experiment is that it shows that light is a wave because light diffracts. So remember in that experiment you have some light, you send the light towards a double slit. A double slit is just an opening with two openings in it. And you can see here that when the light passes through each opening, it changes shape into a sort of a semicircle shape. That change of shape is called diffraction. And remember, this causes the light to overlap with itself. And when that happens, we get interference. So if we look on the screen, we're going to see an interference pattern. An interference pattern is just alternating bright and dark spots. Well, what de Broglie figured out is that if you repeat the double slit experiment with electrons instead of with light, you get an interference pattern. Now, this was a crazy discovery because prior to this, everybody thought of electrons as particles. Electrons being particles, you wouldn't expect them to diffract because only waves diffract. But what you're actually seeing here is that your electrons are creating an interference pattern, which is evidence that the electrons diffracted, which means that these electron particles have wave properties. So if I just go back for a second, the experiments are the same, but they're sort of showing opposite things. Remember, at the time of Young's double slit experiment, this is showing that light has wave properties. Okay, and so we knew that light is a wave from this experiment. But then remember later, when Einstein explained the photoelectric effect, he explained that light is a particle. So the idea is that in some situations, light behaves like a wave, but in other situations, light behaves like a particle. And when de Broglie started to think about that, he thought maybe the reverse is true. So if light, which is a wave, can have particle properties, he thought that maybe electrons, which are particles, can have wave properties. And this experiment, which is called electron diffraction, showed that that was true. So the electron diffraction experiment, again, this is the important part, says that since electrons diffract, electrons are waves. Okay, so what happens if you send one electron at a time through the double slit apparatus? So when you do that, you're going to see a pattern start to build up. So if you look on here, after 100 electrons, you start to see sort of a pattern. So every time an electron hits the screen, it leaves a white mark, by the way. So where you're seeing these white marks, that's where electrons have landed. After 3,000 electrons, you're starting to see something, and it becomes even more obvious down here. After 70,000 electrons, you're really starting to actually see an interference pattern there. So notice how there's some areas that are darker, like right here, that's darker, and there's some areas that are lighter right here. So remember, interference pattern is alternating dark and light spots. Only here it's not light creating the pattern, it's electrons creating the pattern. So the idea is when an electron passes through the double slit apparatus and strikes a spot on the screen glows at that spot. As more and more electrons strike the screen, the spots eventually form an interference pattern. That's what those pictures are showing. Now, this experiment actually shows that electrons are particles and waves at the same time. So since each individual electron hits the screen in just one place, in that way they're acting like particles. But after many electrons hit the screen, they form an interference pattern, and so in that way they're acting like waves. And so what we can say is electrons exhibit or show wave-particle duality. They are waves, they are particles, both at the same time. All right, I'm going to post the link to this video up on D2L for you, and you should go and watch it. So how can we get an interference pattern if only one electron is passing through the double slit or the apparatus at a time? What is the electron interfering with? Well, in 1926, there was a physicist named Max Born, and he thought about this problem and solved it, and suggested that the wave nature of particles is best understood as the probability of finding the particle at a certain location. Now, there's actually a lot of math behind this. If you go on and you take physics in university, you would learn about this math in a quantum mechanics course. We don't have the mathematical tools to really fully explain what this paragraph means, so you're not expected to fully understand it at this level. You just kind of have to have a vague idea of what's going on. So the idea is, if I just go back for a second to these pictures that we had, the individual electrons are acting like particles, right? Because they're hitting the screen in just one spot, like a particle does. If you throw a tennis ball at a wall, the tennis ball will hit the wall in one place, right? It won't land in 5 different places all at once. It will hit in one place. That's what particles do. But when you look at the picture here, which I will put a red box around, anywhere that's lighter, that means more electrons have hit right there. So that means, for example, the electrons had a high probability of landing right here in one of these really bright regions. But anywhere that's darker, the electrons had a lower probability of landing. And the probability, the equation for it is like a wave. And so when we say that electrons have a wave nature, that's what we're talking about. So here's a picture of a wave. Okay, so if this is a probability wave, then electrons are most likely to be where the wave amplitude is high. So remember, amplitude is measured either from a crest to the midline or from a trough to the midline. And so those parts of the wave are showing high probability. And the electron is least likely to be where the amplitude is low. So right here where I'm putting this blue dot, that's 0 amplitude. And so the electron is least likely to be right there. And so I said this already, but on the screen, bright fringes occur where there's a high probability of electrons striking the screen, and dark fringes occur where there is a low probability. And that's the extent of what you have to know there. So this brings us to our last model of the atom that we're going to study in Physics 30, and it's the quantum model of the atom. If we visualize the atom as a nucleus with electron waves around it, then we get the quantum model of the atom. So the quantum model builds on the Bohr model. The energy levels, which are also called orbitals from the Bohr model, are electron standing waves. So I'm going to explain that more in just a second, but here in this picture, this sphere in the middle represents the nucleus, and then this represents an orbital or an energy level. And what I want you to notice is that the orbital looks like a wave, and it's a wave that's surrounding the nucleus. So quantum model vocabulary. So just so you know, if you see a question and it refers to the wave function or the probability wave or probability cloud, all of those things have to do with the quantum model. And so the wave function is the same thing as a probability wave, and a probability cloud, it just means that sometimes we can call the orbits of the electrons probability clouds instead of orbitals, but same idea. So remember I said a couple of slides ago that the orbits are like standing waves that circle the nucleus. Here's an animation of a circular standing wave. So waves oscillate up and down, so that's what you see there, and then your nucleus would be somewhere in the middle. Now, what we can do is we can actually count the number of wavelengths that are in this standing wave. So one wavelength includes one crest and one trough. So, for example, that is one wavelength. So we can go in and we can see how many we have. So there's another one. Here's another one. And then finally, one more. So if we go in and count, each of those sections that I drew is one wavelength. So we have 1, 2, 3, 4 wavelengths total. And what scientists figured out is that that means that this would be the 4th energy level, which we call n is equal to 4. All right, and I'm just going to go to the next slide for a second, and then I will go back to something that I skipped there. So only orbitals or energy levels made of whole numbers of wavelengths are possible. So if you look here, we have some different orbitals on the screen. This one has 3, so that's the n equals 3 energy level. This one has 4, this one has 5, and this one has 6. Okay, and what we do is we take those waves and we wrap them around the nucleus. So looking here, it says the circumferences of electron orbits from n equals 1 to n equals 4 shown straightened out. So for n equals 1, as I keep saying, that has one wavelength, right? And for n equals 2, that has 2 wavelengths. And then you wrap them in a circle. So this is a picture of what your atom would look like. Okay, so your nucleus would be in the middle here, where I'm putting this red dot. That's the nucleus. And then you have your energy levels wrapped around it like that. So there's the 1st, 2nd, 3rd, and 4th energy levels. Now, in order to actually wrap a wave around the nucleus, you have to follow this rule, which I said once already, but it's important. Only orbitals made of whole numbers of wavelengths are possible. So what you see on this slide here is, for example, exactly 3 wavelengths or exactly 4 wavelengths. It's never going to be 3.1 wavelengths or 4.7 wavelengths. It's only whole numbers. And the reason for that is this. So if we go back to this diagram for a second, we see here that we have a wave. So I'm looking at this one. And notice how right here, the wave doesn't join up with itself properly. That's because this is not exactly a whole number of wavelengths. So if we count the wavelengths here, we have 1, 2, 3, 4, 5, 6, 7, and a bit. Okay, and so this wasn't exactly 7 wavelengths. It was 7 plus a little bit. And because it's not an exact number, right there where I'm circling, when the wave joins up, it doesn't join up properly. And so what happens is the wave is going to interfere with itself right here, and that's going to end up destroying the wave, and it won't function properly. And so this actually explains why within an atom there are only certain allowed energy levels. So if we go back to the atom for a second, right? We're allowed to have level 1, and we're allowed to have level 2, and 3, and 4. But for example, in between level 3 and 4, there's no energy level. And that's because in between those levels, you cannot wrap a wave in a circle and have it join up with itself properly. If you try to wrap it in a circle, it will interfere with itself and it will not do what it's supposed to do. So this is kind of what I said already. So non-whole number wavelengths are impossible. The wave would interfere with itself and get destroyed. So here we have a picture of one situation where the wave fits perfectly, and then we have another situation where the wave doubles over on itself. And as I tried to say earlier, the wave will destructively interfere with itself and disappear. So this energy level here is not possible. And so as I was saying, this explains why, like in the Bohr model, electrons can only be in certain allowed orbitals. Okay, so now we're going to talk about matter waves. Matter waves are the type of waves that particles have. So Louis de Broglie showed that electrons have wave-particle duality. We talked about that already, but it's actually bigger than that. Turns out that everything is both a particle and a wave at once. So everything has wave-particle duality. So Louis de Broglie studied matter waves in general. As I said earlier, a matter wave is a wave associated with an object that has mass. The wavelength of a particle with mass is called the de Broglie wavelength. So this symbol right here that I just circled, that's the de Broglie wavelength. Okay, h is Planck's constant, and for Planck's constant, you need to make sure that you are working in the joules second version. So remember, there's two versions of Planck's constant, 4.14 times 10 to the negative 15. That's the electron volts version. So here you need to make sure that you're using the other one, 6.63 times 10 to the negative 34 joule seconds. And P is momentum, which remember, momentum is mass times velocity. So here's an example. So it says, what is the wavelength of an electron moving at 2.19 times 10 to the 6 meters per second? So what we do is we take our formula that we had on the last slide, and we're going to rewrite that, but instead of writing P, we're going to write MV, and that's because P equals MV. By the way, if you're looking on your formula sheet, you're going to see a couple different formulas on there. One of them says P equals mv. That one we already learned earlier in the semester, and that's for particles with mass. There's another one on there, E equals Pc. E equals Pc is only for photons. So E of a photon stands for the photon energy. P is still momentum, but it's photon momentum. So remember, because photons are particles, they can actually have momentum, and c is the speed of light. So it's 3 times 10 to the 8 meters per second. Anyway, you don't need to worry about this E equals PC formula for this lesson. I'm just pointing it out because you should not be using it. So here you should be using P equals mv. All right, so I've plugged in numbers. So because the question's asking about an electron, right here I've got the mass of an electron. And if you go ahead and you calculate that, you get lambda. Lambda here is called the de Broglie wavelength because it's the wavelength of a particle. And the answer is 3.32 times 10 to the negative 10 meters. So you might be wondering, if everything is both a wave and a particle at the same time, why don't objects in our everyday experience demonstrate wave-like behavior? So for example, how come when I throw a tennis ball, I don't see a wavelength associated with that tennis ball? Well, imagine you have a 1 kilogram baseball, but same thing as a tennis ball, moving at 10 meters per second. If we go in and we calculate the de Broglie wavelength for that object, we end up with something that's times 10 to the power of negative 33. That's tiny, 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 tiny. It's actually a lot smaller than this wavelength that we calculated here for the moving electron. And so that wavelength is so small that it's actually almost impossible to measure. But there's another consideration too. Compared to the size of a baseball, this wavelength is so small that we can ignore it. Okay? Wavelength is only significant for quantum objects. So what that means is, for the electron here, okay, something that's times 10 to the negative 10 meters, yes, that's a small number, but electrons themselves are also very, very small. So that means that this wavelength is actually going to have an impact on the electron's behavior, which means that the electron will behave like a wave in some situations. Meaning you can't just ignore the wave nature of the electron, because electrons are small, but the wavelength is also small, and so they influence each other. But for the baseball here, okay, something that's times 10 to the negative 33 is so small compared to the size of a baseball that it's not going to affect the baseball's behavior at all. And so you can ignore it. Okay, so wavelength is only significant for quantum objects. And so in this course, that's things like electrons and photons. So we would say electrons have wave-particle duality, and photons also have wave-particle duality. So what that means is light behaves like a wave, but it also behaves like a particle. It's both at the same time. It's not one or the other. And that's where we'll stop.